Tanner. Hello, this is Tanner Tech.
And in this video, I'm going to be showing you how to build something called a vacuum tube Tesla coil. Now, you've probably seen my videos on me making Tesla coils before with spark gaps. Now, these Tesla coils kind of worked, but they did not work very well. I was only able to get very small sparks. But luckily, just the other day, I was able to stumble upon this gigantic transmitter tube inside an old electronics store. Now, I saw this transmitter tube and I knew I had to build a vacuum tube Tesla coil. So that's what we're going to do in this video, and hopefully it's going to be awesome. So this is all the stuff you're going to need to build this gigantic vacuum tube Tesla coil. First and foremost, you need a vacuum tube. This vacuum tube is an iMac 3X2500F3, and this is a transmitting tube rated at 5,000 watts of RF power. You're also going to need a lot of microwave transformers, namely these two microwave transformers. They haven't been modified at all. They're 2,200 volts, probably AC. You're also going to need a rewired microwave transformer. Now, this transformer has a few turns of wire, and this wire is meant to power the filament of the vacuum tube because this filament takes 48 amps at 7.5 volts. So that's quite a bit. You're also going to need to have some microwave capacitors and some microwave diodes, lots of wire. You're going to need to have a secondary coil for your Tesla coil. This thing is about maybe 500 turns on a piece of PVC pipe. You're then going to need some capacitors, resistors, and finally you're going to need something to mount your Tesla coil on. So I'm here in the electronics warehouse. I'm getting some parts. As you can see, they have every single capacitor you could possibly need. And luckily, they have 500 picofarad, 5,000 volt capacitors. And so I'm going to get a bunch of these things, along with this really cool forced air cooling fan. Cool my vacuum tube, along with some of these capacitors, telegraph key, a big power resistor. I'm loading up on these little capacitors. Look at these boxes. I just made these fingerprints. These things haven't been opened in years. Now this right here is my platform that I'm going to be building my Tesla coil on. These PVC pipes are for the primary coil of the Tesla coil and the feedback coil. And this piece of wood right here is a mount for the vacuum tube, so I'll mount that right now. Now this is a schematic of what this Tesla coil is going to look like. Well, that's enough talk for now. It's about time to start building this thing. I'm going to start by mounting some of the transformers to this wooden base, namely the microwave transformers, and I'll bolt these things down, and that should be good. I'll then maybe wire the filament, start winding the primary coil of that. Maybe I need to make a capacitor bank here too. These are 5 kilovolts, 500 picofarad capacitors, so these need to be connected in series and parallel to form a bank to those desired capacitor values. I've also got this cool resistor. This resistor is the plate resistor for the vacuum tube, and this is going to be forming the plate inductor choke. So I'll just wrap this wire around here 14 times, and yeah, that'll be pretty good. Alright, so I got a lot accomplished with the vacuum tube Tesla coil. So I wound some wire on this resistor. I got about 13 turns around it. So this will be the plate, resistor, and choke. I've also got the entire filament set up, wound. I have the vacuum tube. It's securely mounted in the frame. And then I have this little insulator bit made of PVC pipe, and the insulator bit is bolted onto the two filament leads, and those two wires go down to my filament transformer, which is a rewound microwave transformer. So this thing is already super heavy. Now it's time to add some more things, including this, which is going to be the forced air cooling fan. It's going to sit underneath the vacuum tube to force air cool it. And I'm also going to start winding the primary coil of that, which is going to be a little bit difficult. Well, as you can see, the primary coil and the feedback coil are done. We've got these two wires, and these two wires go to the feedback coil. Then we've got this black wire and this white wire, and these wires go to the main primary coil. We also have this center tap and this center tap for the primary coil. This one is at 20 turns and this one is at 10 turns. So that's just for future use if I need to. So now it's time to move on to another part of building this, and that is the power supply. And for that, I'm going to be using some of these power cords and making an external box with switches on it, so that way I can also soft start this tube filament heating up, because it's not good to hard start it, so I'll soft start it through an 8 ohm resistor. As you can see, I have all the supplies to make the switch box. I'm going to be using this little piece of wood as part of the switch box. I'll also be using these 3 switches and this plug as part of the soft start switch circuit. I also have this really gigantic plug that I'll hook up to some Romex cable, and that cable will go to this plug and go to my switch box, and my switch box will plug into the Tesla coil, and I will soft start it using this 8 ohm resistor. So let's get started building this whole thing. This is the switchboard right here, and this is basically the controls that allow us to turn on and off the circuit. Underneath is just 3 switches and 1 plug, and I've got my soft start resistor down here. Now let me show you the soft start feature of this. So we have the bypass off, so it's soft starting. We turn it on, you see it start to glow. As soon as I kick off the soft start, then you see it glow even brighter. So that, as you can see, the soft start works extremely well. Well, now that I've got all the low voltage stuff, the 7.5 filament voltage, and the switchboard, 120 volts AC, let's start to get to the high voltage with these microwave transformers. Hook those up, bolt them down, and wire up some of our capacitor banks. We need to make a capacitor bank first. I've got a whole bunch of small capacitors that need to be banked. So I'll make some capacitor banks and hook up my resistors, namely this large high wattage resistor. Hook up everything to the Tesla coil circuit, and hopefully we'll get a really cool looking vacuum tube Tesla coil. Alright, so I've finished my capacitor banks that I will need for this Tesla coil. So first of all, I have the main capacitor bank for the tank circuit, and this capacitor bank is approximately 2 picofarads at 15,000 volts, and they're all ceramic pulse capacitors, so this thing should work fine and not blow up or overheat. I've got this small little bank. This is for the grid leak circuit. This is about 3 nanofarads at 5,000 volts. And then finally, I have this capacitor bank, and this is the filter capacitor bank for the power supply. And this is 12,000 volts, and it is rated at about 10 nanofarads. So those are my 3 main capacitor banks. I made these using capacitors that I got from the electronics warehouse. They had a gigantic box of these 500 picofarad 5 kilovolt capacitors, and I just grabbed a whole bunch of them. Now it's time to take a look at the Tesla coil and add the cooling system. So in the data sheet for this vacuum tube, it says that you need to add a cooler fan to the stem of the vacuum tube where the filaments come out at. So that's what I made this fan for. This fan will sit up here and it will blow straight onto the filament stem, hopefully cooling it off. It says he needs 3 cubic feet of air per second. Then you've got the one on the bottom that blows through the anode cooler, and the data sheet says that this cooling fan needs to have 120 feet per second, cubic feet per second. I'm also going to have this fan, and this fan is going to be cooling the transformer right here, and everything is going to be powered by this 12 volt little switchboard power supply. And that's going to plug into a separate plug, then the filament transformer and power transformer, because the cooling fans need to come on before the tube warms up, and they need to stay on for 5 minutes after the tube is off. So let's get started installing that cooling system, and I'll get back to you when it's done. Alright, so the Tesla coil is coming along very well. We've got the entire cooling system wired up. We have this little wall plug adapter hooked up to all 3 fans, and so everything can be properly cooled. Right now I'm working on installing the high voltage power supply with this capacitor bank is the filter one. This microwave capacitor is the Doppler capacitor, and everything else. So yeah, it's a little bit of a tricky thing to accomplish, but yeah, at least that's done. So let's get working on the high voltage. Alright, so I am extremely excited because I have finished my vacuum tube Tesla coil. It is completely done. As you can see, there is a gigantic mess on my floor. I've got wire strippings, wire cuttings everywhere. The vacuum is going to have a heyday cleaning this floor, but all the high voltage is wired, all the capacitors are in there, all the resistors. You know what, let's clean up some of this mess on the floor so that way we have a clean place to run the VTTC. Here we go, and we will clean it in 3, 2, 1. Well, if we look right here, we can see that everything is pretty cleaned up. So now it's time to hook everything together. So I'll set aside the schematic, and we've got our 2 power wires, actually 3 power wires. So we've got the power that goes to the filament. We've got the power that drives the plate voltage. We've got the power that drives all the fans. Now, I'm not feeling too good right now. My stomach hurts, so we'll try this in just a second. So first off, I'm going to start this Tesla coil up by firing up the cooling fans. As you can see, everything's nice and cool. It's very loud, but it's running. We got nice airflow past everything. I'll start by turning on the filament through the bypass resistor. Then we'll turn off the bypass switch. And the vacuum tube will begin to glow at full power. All right, now I'm pretty scared. We've got the plate voltage switch right there. So if anything blows up or if I die, well, you know where to find me. Switching on plate voltage in T-minus 5, 4, 3, 2, 1, go. Nothing. Interesting. Alright, now I can confirm this thing is kind of working because as you see I have a CFL on the top. When I turn on the plate voltage, the light bulb lights up. So obviously something is working inside here and I'm not sure exactly what it is. So let's try that again. As you can see, that's lighting up the light bulb from pretty far away. I'm pretty far away from this. Oh crap! There's a big corona discharge on the feedback coil. Alright, as you can see, when I turn on the plate voltage again, you can see a little bit of a discharge coming off. And this thing is pretty powerful. Oh, crap. Alright, now an interesting thing is when I run this, you can see a blue corona discharge form on the feedback coil. So that's interesting. Alright, now I'm sorry for all the noise, but these fans are just super noisy. And I have to keep them on while the tube is on, otherwise the tube will overheat. So what I'm going to do is I'm going to first unplug the plate voltage supply, and then I'm going to adjust the grid leak resistor, and perhaps we can get a stronger device. Alright, here it goes again. I've got some things adjusted. Hopefully, with a little luck, we should get working Tesla coil right now. Let's give it a run. Ooh, even less. Very interesting. Alright, let's see what this baby does now that I adjusted the grid leak circuit. The grid leak resistor is now significantly lower. Alright, it's cooled down enough. Alright, let's take a look at some of the repairs that I made to this device. So first of all, this capacitor, this little filter capacitor, completely got rid of it. So that is no longer there. We just have a diode and a microwave capacitor for the voltage doubler circuit. I also got rid of the grid leak circuit as suggested by Dimitri. I forgot his last name. But he emailed me and he was trying to explain how this would make my vacuum tube Tesla coil work better. So I basically just grounded this and bypassed this capacitor and this resistor, so the entirety of the grid leak circuit was gone. Now, what I did have to do is I had to change the amount of turns on the feedback coil. So what I did is I just changed this to about 6 turns, and these 2 modifications were suggested by the person who contacted me via email. Now, if we take a look at the way this circuit works, basically we just have a voltage of about 2300 volts here. That voltage goes through this capacitor and this diode and is doubled, and basically how that works is during one half of the cycle the current flows this way through the diode and charges the capacitor, and then the other half of the cycle the current flows the opposite way and the capacitor acts in series with the transformer, and that provides a doubled voltage of this. That voltage then goes through this primary coil and tank circuit, which is 27 turns. Well, it's adjustable. Right now I think I have it at about 20 turns. Now that current goes through this choke, which is a resistor and an inductor. This choke is basically to protect the vacuum tube if anything arced inside, which would be very bad. This capacitor is still 2 nanofarads, and then we have the feedback coil. and that goes to ground. This bypass capacitor that goes between the cathode, the two parts of the filament, that capacitor is still 0.22 microfarads. Now basically what happens is when this device starts up, a large current is going to flow through this coil, through the vacuum tube, and to ground through the cathode. Now that's going to create a large magnetic field inside the primary coil. When that large magnetic field is induced, it will induce another magnetic field into this coil, and that is going to basically make this point go very negative. So it's going to negatively bias the grid. Once the grid is negatively biased, then that'll prevent the vacuum tube from conducting, which will make this primary coil stop having current flow through it. It will collapse the magnetic field. Now, even though the magnetic field is collapsing, it's still going to oscillate because there's a LC circuit inside here with a capacitor and an inductor. And so we're going to have that initial pulse, and then after the initial pulse, it's going to start oscillating. And then by the time it keeps oscillating, there's no magnetic field inducing any current into this coil. And so the grid is then again going to go positively biased, which is basically going to start the cycle all over again. So this fluctuating magnetic field inside the primary coil in this Armstrong oscillator is going to induce very high frequency, high power current into the secondary coil, which is going to make the arcs come off the top in the form of really cool lightning. So as you can see, I removed all the unnecessary items. I have removed the grid leak resistor and capacitor. I removed the filter capacitor right here, so everything's kind of simplified down a little bit. Now I like to share the issues that I had when building my Tesla coil. Now one issue was with this capacitor right here, and this capacitor, as you can see, arced through, and the reason why this arced through is because I had some wires that were too close to each other in this capacitor bank, and so you can see the arc went here, and it kind of shorted out the capacitor bank and caused the full brunt of the load of the vacuum tube to be forced through the capacitors, which blew up that little capacitor. I've also had some other issues with this Tesla coil, such as right here when some of the current arced to the feedback coil. Now another issue that I had is when I was running this thing originally, I had a feedback coil made of thinner gauge wire, around here 27 times, and that created a very high voltage. And actually two of the windings in the feedback coil arced to each other, and those kind of created a big burnout, and it kind of burnt my feedback coil, and that was not good for it at all. So I have a new feedback coil than I originally had. That feedback coil, as you can see, goes directly to ground, no grid leak circuit. Now, another interesting thing is that if you look in the bottom of this little container, there's a lot of dripped wax on there, and that's because during the operation of this Tesla coil, these capacitors overheated by a long shot, and when they overheated, they became so hot the wax that was coating them dripped down. And so I don't want these capacitors to get really hot again, so I went down and I bought some mineral oil. Mineral oil is a non-conductive substance, and I can just fill this little container with mineral oil, and hopefully that'll allow these capacitors to be cooled during the operation of the Tesla coil. Alright, let's fill up this capacitor bank with some mineral oil. We can see the resonant frequency of this Tesla coil by using this small little solenoid hooked up to my oscilloscope, and we can use the oscilloscope screen to figure out the resonant frequency. So I will turn on the Tesla coil, and you'll see a small sine wave come on here, and then as the Tesla coil warms up because of the current between the plate and the cathode, then you will see the sine wave become bigger, and that's why you see the streamers start very small in the VTTC, and they grow larger as time goes on. So let me show you that. As you can see, this device is operating at a frequency of approximately 0.45 megahertz or 450 kilohertz. Now, as always, thank you for watching and stay tuned for my next video. So, this Tesla coil worked really well. It took a lot of trial and error and a lot of different approaches to solving the issue, but I was eventually able to get a very cool working Tesla coil. So, thank you for watching. Stay tuned for next time.